right, so I'd like to continue Chapter 8, talking about many electron atoms Part 2. You should have watched first the Crash Course Chemistry video that's on the history of the periodic table, so I'm picking up after that. Hopefully you enjoyed that. It's a fun video. I really like the way that he presents things and he really gets into the history of Mendeleev, which is awesome. Okay, but I'd like to go into a little bit more depth about the periodic table and what it all means and some of the patterns that Mendeleev noticed. So first of all, a little bit of vocabulary. If you didn't already know, the groups in the periodic table are how they refer to the vertical columns. These groups have the same number of electrons in the L orbital, and therefore they form similar chemical bonds. The periods are what they call the rows, and that corresponds to the filling of the subshells as you walk across. Now there's two important points that I'm almost going to quote verbatim from your textbook because I really can't think of a better way to say it. So filled subshells are normally very stable. Atoms are going to want to move towards stability. So an atom that's, for example, one electron beyond a filled shell, as there are in the alkali metals, that will readily give up its electron to another atom. And if you have an atom that's only lacking one electron to where it's a filled shell, like the halogens, then that will readily accept that one electron. This makes those particular groups in the periodic table very reactive. Now, filled subshells don't normally contribute to the chemical or physical properties of the atom, and only the electrons in the unfilled subshells need to be considered. So when you're thinking about properties such as the magnetic properties, the electrical or conductive properties, or the chemical reactivity, you really don't have to think about the electrons that are in the filled shells underneath, only the valence electrons in the outermost shell. All right, so let's start going through some of the properties. Some of them are pretty easy to understand and see. So this is figure 8.7 from your textbook, and in this it shows the values of the atomic radii. Now, how do you determine an atomic radius, right? Because as we saw from looking at the wave functions, the radial wave function, it's kind of fuzzy, right? The orbits sort of extend off and decay off very slowly, and it's really an electron cloud. So the way that they usually determine the radii for an atom and what they call the radius, a definite number, is if it forms a solid, what the crystalline spacing in between the neighboring like atoms are, okay? And that's how they say, okay, well, this distance between the center of this atom and the center of this atom is the diameter of the atom, and we'll call half that the radius, and that's what they do, okay? So that's how these radii here were determined. Now, if you look at this, you can see in this plot that there's definitely a periodicity. As you start off in the period, in the row, you start with a very large value and it decays off to a small value, and then it picks up again in the next, and the next, and the next. Okay, so what's going on there? This may at first seem strange because what this plot is telling you is that some of the atoms that have more electrons can actually have a smaller radius than an atom with fewer electrons. So for example, if you look at this first little plot here, you see it starts off with lithium, which has 3 electrons, and then as you add electrons on, the radius actually drops, which seems strange and counterintuitive. But the reason that happens is that as you fill your subshell, then your atom is more stable, and more stable configurations are more tightly bound with smaller radii. So you can see that your alkali metals, in other words, the first column of the periodic table, lithium, sodium, potassium, and so on and so forth, those are all the ones with the largest radii from that particular row of the periodic table. Now the ionization energies here, first of all, to define, an ionization energy is the amount of energy that's required to free that valence electron that's in the outermost orbital, okay? Now, if you can remember the plot on the previous page, it almost looks like the ionization energies are sort of the inverse. The ionization energy plots are sort of the inverse of the radius plot, and that is not an accident, and it's for exactly the same reason. If you have a filled subshell, those electrons are more tightly bound, and so it takes more energy to liberate those electrons, okay? So it takes more energy to free it. Whereas if you have something that's very weakly bound, then it doesn't take much energy at all to get rid of it. Okay, now the valence electrons also get easier to free as your number of electrons or protons in your atom increases, okay? So as Z increases, so does the number of electrons, and therefore the value of their energy level goes up as you add more electrons on. So here you have sort of two layers of structure in this plot. You've got the periodicity within the rows of the periodic table, and you see that sort of jaggedness according to the periodicity. But according to, as it walks through the group, that changes. But then you also have this sort of overall decay to where it decays off to sort of a limiting value here at the end of the plot, and that's due to this value of N increasing as you add more electrons on. So there's two bits of structure there. Okay, now your inert gases, your helium, your neon, your argon, your krypton, your xenon, so on and so forth. Those are the last group of the periodic table, and those are the ones that have totally filled p subshells. Okay, sorry about that, we're back. So your noble gases, your inert gases, the last group of the periodic table, they have totally closed and filled subshells. So this makes them very, very non-reactive. They're boring, actually. They're terrible conductors. They have very large ionization energies. And because you have a whole bunch of electrons that are all paired up and down spins, they have a zero net spin. Because they have zero net spin, they have really low magnetic susceptibilities. So they're not very magnetic either. Because they are so happy just to be themselves, they interact very weakly with each other. And that means that when you get a lot of it, enough to make a container or whatever, they're going to have very low boiling points. So they'll stay a gas for a super long time. In fact, liquid helium boils at 4 Kelvin. So it goes from a liquid to a gas at 4 Kelvin, a very low temperature. Neon at 25 Kelvin. Argon at 84 Kelvin. So you can see that these things stay gases for a very long time just because they very weakly interact. Now, they're actually so non-reactive that it was really difficult to discover them in the first place. Argon, for example, makes up about 1% of the air we breathe, so you'd think that people would know about it, but it's so non-reactive that it wasn't isolated and discovered until 1895, and the noble gases weren't put in the periodic table until 1902, so that's a pretty interesting little factoid about a really boring set of gases. Now the alkali metals are much more exciting. Okay, these are the ones in the first column of the periodic table. They have a single s electron that's outside an inner core of electrons that are all happy and bound up. So that electron would really like to just go away so that you have a very stable configuration of electrons underneath it. So that electron goes away very easily, which makes the alkali metals really super chemically reactive. They also have very low ionization energies for the same reason, and because they have that single electron that they would like to donate, this makes them excellent conductors of electricity as well. In fact, alkali metals react so violently that if you put them in something like water, then they react very quickly and violently to form a metal hydroxide and hydrogen gas. And then the hydrogen gas, of course, is very flammable, so oftentimes you get explosions, as is shown here in this picture from a YouTube video. To avoid reacting with the oxygen in the air and the water in the air, you actually have to store alkali metals when they're in their pure form under oil, which is kind of an interesting little factoid. And in the Earth's crust, because they are so reactive, they're really only found as salts. The alkaline earths are a little calmer, okay? These have 2 s electrons in the outer subshell. They're still somewhat chemically reactive, so in the Earth's crust, they're generally found in compounds and in minerals. They're really common, by the way, especially calcium, magnesium, things like that, very, very common metals. They have large atomic radii because the 2s electrons sit outside more tightly bound inner cores of electrons that are very happy to be there, so they have pretty large radii. And they like to donate those electrons, so when they're in their own form, they're good conductors. They're all shiny, silvery white, and somewhat reactive metals at standard temperature and pressure. Here you can see some images of what they look like in their pure form. However, as I said, they're generally not in their pure form because they are kind of reactive in the Earth's crust, and usually you find them in minerals. Now, if you want something reactive, though, the halogens are also quite reactive because they only need one more electron to fill that outermost subshell. So strong ionic bonds can be formed with the alkalis. Like the alkalis want to give up that electron, the halogens want to accept that electron, so they very quickly react together when they're put in the same area. And they form salts, and actually the word halogen means salt producing. If you put them with hydrogens, they form acids. You've probably heard of hydrochloric, hydrofluoric, those kinds of acids. They're very strong acids. In small concentrations, these ions are actually beneficial for people, right? Fluoride in your toothpaste, things like this, it's not bad for you. But in large concentrations, not so much, right? Very bad for people in those concentrations. The transition metals, these are the ones that you're filling up your d orbitals. So they're shown here in the purple on this little periodic table. The properties of these things are primarily determined by the s electrons that are to their left on the table. And that's because the s electrons have a larger orbit, so they're outside the d subshells that are getting filled up. So it's kind of an interesting dynamic. And because the s electrons are on the outside, those are really the valence electrons, and so they dictate a lot of the properties. And so that makes the transition metals all kind of the same as you fill in the d orbital, because the s electrons are really sort of controlling the day and they're further away from the nucleus. Now, transition metals can actually make decent magnets. You have some ferromagnets in the transition metals. And the reason for that is the Hund's rule that we talked about in a previous lecture. Remember, if you've forgotten, Hund's rule says that electrons are going to fill up orbitals, the ml values in other words. They're going to fill those such that the spins are going to remain parallel as long as possible. So for example, it's going to go in orbital where ml is equal to -3, and then it'll go in the -2, 1, and then -1, 1, oriented so that the spins are all parallel as you fill it up. Now, those spins, remember, your spins give you a magnetic moment, and those magnetic moments are going to sum up to be a large net magnetic moment for the element itself, okay? So if you have a large magnetic moment for the atom and then you put a bunch of the atoms next to each other, those magnetic moments will tend to align with one another, and then you have yourself a ferromagnet, okay? Now, as the d subshell gets filled, though, some of those unpaired spins pair up, and then you have a lower net magnetic moment, and so as it gets filled, it's not as magnetic. Transition metals can also be good conductors. In this plot, we see the resistivity plotted versus the value of Z. And you can see that the resistivities for the transition metals are generally pretty low, except for the shells which are half-filled, which seem to be more stable and cause a lower conductivities. Now you can see here that there's dips in this plot, very low dips, and those very low dips in the resistivity occur for very good conductors. Remember, resistivity and conductivity are inverse of one another. So here you see copper, silver, and gold being the very low points on these plots. Well, those are interesting special cases. They all occur in the same group on the periodic table, the same column, and what's going on there is that instead, for example, for copper, instead of a configuration of 4s2 3d9, it would really like to fill that D subshell, and so it takes an electron from the 4s2 to become 4s1 3d10. And then that, remember, the s electrons are on the outside. That s electron is very weakly bound, okay, very weakly bound. And so it's free to join the free electron C and carry current. And since copper, silver, and gold are all in the same group, all in the same column, it's kind of the same story for the silver and the gold. Okay, this brings us to the end with the lanthanides and the actinides. The lanthanides are also called the rare earth elements. The lanthanides have a lot in common with the transition metals in that you have the filled s orbital in, for example, the 6s2. That subshell is outside the 4f's, okay? So it's dominated, the effects are dominated by the outer valence electrons of the 6s and not the 4f's that are building up on the inside. And so the properties for the lanthanides are all very similar because the outermost orbital is already filled. So as occurs though in the 3D subshell, you have these electrons that are filling in, and according to Hund's rule, they line up so that the spins are parallel, and that can give them large magnetic moments, and so that can make large ferromagnetic effects for the rare earths. You've probably heard of rare earth magnets. I show a picture here of a rare earth magnet with a ferrofluid kind of on top, making a cool pattern showing the magnetic field. And you've probably seen things like that. Now the actinides, they're a little bit more difficult to pin down because they're large elements. They're radioactive. We're going to discuss this more in a later chapter when we deal with radioactivity. But you can know, looking at the periodic table, that as you get a larger and larger nucleus, it becomes more and more radioactive. It's more and more likely to be radioactive. And the actinides are such large nuclei that a lot of them are radioactive. And so it's really difficult to say what the other properties of the elements might be because they don't stay themselves long enough to figure it out. There's a few that do have longer half-lives like thorium and uranium, but most of them have relatively short half-lives and so decay into something else before too long. All right, that concludes what I'd like to say about the periodic table. Yet again, remember, this is combined with a lecture that came from another website that I wanted you to watch earlier, and hope you enjoyed it. Let me know if you have any questions.